Hey, welcome back to your favorite trig class. Let's continue on here. Let's go scalar times this vector v. So 2 times vector v would be 2 times the 4i plus 2j. So 8i plus 4j. Or you can think of it as 2 times its components 4, 2. So 8, 4. So to give you a picture of that, you have vector v. This is components 4, 2. So here's our position vector v. Right, 4, 2. But what it does is it doubles that. So it goes another to the right 4 and another up 2. So here's in red 2 vector v. Okay? Where you end up, there's your components for that 2 vector v. Double vector v. So it doubles the magnitude, right? It goes in the same direction. So let's do 3v minus 2w. So 3v, 4i plus 2j, minus 2w, 2i minus 3j. So we got 12i plus 6j minus 4i plus 6j. 12i minus 4i, we got 8i. 6j plus 6j, we got 12j. So 8i plus 12j. Or again, you can go component route. So you've got 12, 6, and then 12 plus that negative 4, comma, 6 plus the 6. So we've got 8, comma, 12. Right, again, notice 8, positive 12 on those components. Now, finally, this is the magnitude of vector v. So vector v in black. So here's vector v, right? 4, 2. So here's vector v. In other words, it goes right 4 and it goes up 2, right? So we've got this right triangle. So for vector, the magnitude of vector v would just be find the hypotenuse. So in other words, 4 squared plus 2 squared equals c squared. So c, which is, in other words, the magnitude of vector v, is the square root of 4 squared plus 2 squared. That's what vector v is. Square root of 4 squared plus 2 squared by the Pythagorean theorem. So 16 plus 4, we got 20, square root of 20. So we got 2 root 5 is the magnitude or length of the directed line segment. 2 root 5, square root of 20. So between 4 and 5, 4 point something. All right, a unit vector. So the unit vector, we can take a vector v and divide it by its magnitude, and we would have the unit vector, right? So for example, if I have a vector that's a length of 5, if I take 1 over 5, the magnitude, times this vector that's a length of 5, right? I'd have a overall length. In other words, I multiply by a fifth, I cut it down, I just have the unit vector, which is the length of 1. Okay? So let's find a unit vector in the same direction as this 8i, 6i minus 8j. So number one, what we're going to do is we're going to find the magnitude. So the magnitude of this, right, because this thing goes there's our vector v, right? So the magnitude of vector v, 6 goes down, 8, right? So square root of 6 squared plus our vertical component, 36 plus 64 is 100, square root of 100, we got 10. Okay, so right now, this has a length of 10. So what we're going to do to find the unit vector, so the unit vector, would be this vector divided by its length, its magnitude. In other words, 1 over the magnitude times the unit vector. So that's what we're going to do. We're going to say, well, let me cut this. If I take this length of 10, I cut it, or multiply by 10th, I divide it by 10, 10 divided by 10, we got 1, right? So we go 1 over, so I'm doing this right here, the magnitude, times vector v. Well, vector v is 6i minus 8j. Then we distribute that, so we got 6/10 I minus 8/10 j. So I got 3/5 I minus 4/5 j. In other words, 3/5 is horizontal component, negative 4/5 is the vertical components on that. So that or that. That's our unit vector. Let me draw what that unit vector looks like. So it goes 3/5 to the right, down 4/5, so it's like right here. Oops. So there's our unit vector. So this unit vector only has a length of 1. Its magnitude is only 1. Because we took this long 10, we cut it, we divided by 10. So then we're just left up with the little unit vector that only has a magnitude of 1. Okay. All right, now if a vector represents the speed and direction, it's called a velocity vector. If it represents direction and amount of force, it's a force vector. Okay, so here's our equation for these vectors where you've got an alpha being the direction angle for the vector, v, and I and j, the unit vectors there. Okay, so let's do an example with this. So for example, we got this ball. Ball is thrown with an initial speed of 30 miles per hour. So number one, I'm going to say, first of all, that's my magnitude. Okay, that's the magnitude. So this vector is representing this speed miles per hour, 30 miles per every hour. That's our magnitude. So that's the length of it. The length of this vector is representing how fast this ball is thrown. Okay, so it's a length of 30. If it was a shortened length, it'd be a slower speed. There's a longer length that's representing a longer speed for this vector. Okay. Number two, they give us this angle. This angle, it's an angle of 45 degrees with the positive x-axis, with the horizontal axis. So if you're drawing a picture of this thing, you've got this ball being thrown at this alpha being 45 degrees, and the length of this, I'm going to say 30 miles per hour. So this length, however long that is, represents that speed. Okay. So then we're just going to use that vector v. We're going to use this right here. Is the magnitude times cosine alpha I plus sine alpha j. That's our vector v that we're going to have on this thing. So our magnitude is 30, and then it's times cosine, angle's 45 degrees, sine 45 degrees j. This is an I, a really bad I right there. So we got 30 cosine 45 root 2 over 2i, sine 45 root 2 over 2j. Distribute the 30 through to both of those. So we got 15 root 2i plus 15 root 2j. So that's step one. Now step two on this thing, these were just kind of our side notes on that. What's the initial speed in the horizontal direction? So the initial speed in the horizontal direction is the horizontal component. So that's the 15 root 2 right there. So the initial speed in the horizontal direction is 15 root 2. Or if I punch that in, 21.21 miles per hour. 21.21. Number three, the initial speed in the vertical direction. That's the vertical component to this thing. Initial speed in the vertical direction. Again, that's the 15 root 2. Also happens to be 15 root 2, or 21.21 mile per hour is the vertical component, so the initial speed in the vertical direction. Alright, let's find a direction angle of 6i plus 3j. Say we have 6i plus 3j, so we have this position vector. It goes to 6, 3 here. Here's our position vector. And here's our alpha. So we're wondering, what's our alpha? Well, we know this is 6, that's 3. We've got this right triangle. So what I'm going to do is I'm going to say, well, I know the tangent of alpha. Let me use the tangent because it's opposite over adjacent. So the tangent of alpha is 1/2. And then I'm just going to run the arctangent on both sides of this thing. So arctangent, arctangent. So alpha is the arctangent of 1/2. I punch that in, make sure you're in degrees here. Let's see, and I'll get 26.565 degrees is the direction angle for alpha. Oops, oh, 26.565 degrees, okay, or 26.6. Now, a couple notes here. We don't get into this stuff in this course, but resultant force. If force one, if vectors F1, subscript 1, and F2 are two forces simultaneously acting on an object, the vector sum is the resultant force. Okay, so that's the same effect on the object as when the two forces act on the object. Okay. And finally, static equilibrium occurs if the object at rest and the sum of all forces acting on the object is 0. In other words, if the resultant force is 0, if your resultant force is 0, then the object is said to be in static equilibrium. Thank you so much for watching. We will see you guys next time.